A recent groundbreaking study reveals that the organic building blocks essential for life may be preserved on the Moon. Elements vital for life, like carbon, nitrogen, and oxygen, were delivered to Earth and the Moon during the early solar system. These essential elements were delivered via asteroids and comets impacting the surfaces, potentially providing the building blocks for life's origin on Earth. Extensive geological activity on Earth erased these early records. The Moon, however, acts as a natural time capsule preserving evidence of extraterrestrial organic matter. A new study has systematically identified multiple nitrogen-bearing organic species on the surfaces of lunar soil grains. This marks the first systematic identification of these specific organic compounds in lunar samples, shedding light on the origin and preservation mechanisms. The research analyzed lunar soil grains returned by China's Chang'e 5 and Chang'e 6 missions, enabling this in-depth analysis. The study reveals a fascinating evolutionary pathway for these organics, from delivery to modification. This pathway involves exogenous delivery, followed by modification through impacts, and continuous processing by solar wind on the airless lunar body. Researchers selected the lunar soil grains for in-depth analysis to understand the morphology, origin, and preservation of nitrogen-bearing organic matter. Multiple microscopic and spectroscopic techniques were used to characterize the chemical bonding, functional groups, and isotopic compositions of the organic matter. The organic matter exists in three primary forms on the lunar soil surfaces: particle-like, surface-adhered, and inclusion-like. Chemically, these organic materials are dominated by carbon, nitrogen, and oxygen, and are generally amorphous in structure. Amide functional groups were also identified in some samples, indicating complex chemical composition beyond simple carbon structures. These observations suggest that lunar organics have undergone more complex chemical reorganization, not merely existing in the highly ordered form of graphite. Further analysis looked at the stable isotopic compositions of hydrogen, carbon, and nitrogen in these lunar organics. The isotopic signatures were found to be generally lighter than those reported for organic matter found in carbonaceous chondrites and asteroid samples. This isotopic signature suggests a consistency with evaporation and condensation processes triggered by impacts that delivered organic materials and induced decomposition and recondensation. The Moon truly serves as a crucial celestial body, recording not only the history of organic material delivery, but also the subsequent modification on an airless world.